start, playing around with things. So you don't get you don't get a practical proof of the soundness of the system.
I see.
Yeah.
So why did you say that tying the or defining the type inside of the trait is something that you want to do? So for my implementations, I just had two different types that were each sort of had or two different traits that each had classes that were parametric in the types of the other.
Yeah, exactly. But then what you have to do is, like, if you want to keep it clean, you keep them totally independent, and then at the end you make a final trait that joins the two.
Got it.
Yeah. And that's kind of, so I figured this out entirely on my own with using the OCaml module system. And then I later learned that this technique is called tying the recursive knot. So yeah, I've done it 3 times. So I've done it with the OCaml and their module system. I've done it with the Scala version, and I've done it with Haskell.
Where is the Scala version?
Let's see.
I've seen the OCaml.
Yeah, the Scala version I have probably just local to my machine here. Let me see. I don't know if I have it on my laptop. I have it on one of my machines at home, but let me take a look. Okay, there's that. All right, so I have to see if I can mount one of the other machines. 1 second. Okay, looks like I'm in, and then users, work, source, projects. And then shoot, where is it? Huh. Let me go back one and see. Maybe I have it. Okay, let me do it this way.
Yeah, no big deal if you can't.
Yeah, I can't find it right now. I'll look for it and post it so that everyone can see the solution.
I'd appreciate that.
Yeah, and for the Haskell version, That's on Akbar's Grasp, and I could find that very quickly. I did a couple of different versions. The Akbar's Grasp version is very straightforward. Let me just head over to um, uh, head over to the repo here, and I want to look for Ek.
And I just put the OCaml in the chat.
Yeah. Let's try. Here we go. All right. So I'll do a screen share now, and then we can get started. So let's go ahead and rock. And Christian, I'm ready to record now.
Yeah.
Okay. So now I'll do a screen share. And let's see, this is probably too small. But you can see that the repo is Akbar's Grasp and row machine inside there. And so essentially there's a notion of a nominal, which is a type class. And there's a notion of a name which implements nominal. So the type class has a code and which takes a P and returns an NFP. And so then code is just the code. In the case of name, I've given it 2, so you can see that you can inject, because I was using this to build a piece of hardware. So I wanted to have names that were addresses and names that were codes of processes. So that's the 2 different type constructors here. And so then code, the implementation of code for the nominal is just the code type constructor here. And then likewise, we have a type class nominal, a behavioral that depends on nominal. And then this gives you all the abstract constructors. And then process, which derives nominal, and you can see that here. But so process is parametric in X in the same way that name is parametric in P, right? And we have no notion what a P is, and we have no notion what an X is. We just know that if we had one, we can make these things, right? So these two things are completely distinct. They're separate. And this is what you want to do in Scala, but it doesn't work out. And then in the case of Haskell, you tie the recursive knot. And it turns out it's important to have this extra disambiguator if you want to be able to actually make processes. Because you could just do, process, name, row process, but it becomes impossible to, you don't have witnesses for the reflective case. So you actually have to have this extra tag in order to instantiate things.
Sorry, what do you mean by witnesses? You mean it's like impossible to tell whether it's a name or a process, or what's?
No, you can't tell that it's a type row process. So it'll if you try it out, like load this up and make another one, data, R process equals process name R process, and then try to make things, try to write code. And what you'll see is that the compiler cannot disambiguate the fixed point. It's always constantly thinking that you're of class, process.
Okay, yeah, that makes sense. Okay, yeah. Without it, I see how it.
So you got to have the tag, and the tag bears witness to the fact that you've got the fixed point. And that turns out to be interesting, right? I mean, it's interesting because you really, in order to have, you can tie the recursive knot, but you can't use it without the witness. So that's a flavor of the kind of thing that goes wrong in Scala. So that's a basic implementation. Then you can see some a variety of pieces of code in here. Like here's an implementation of substitution. Here's an implementation of de Bruinification, right? So I do an unusual form of de Bruin indices. It's 3-dimensional instead of 2-dimensional because I'm interested in what happens when you go into a quoted name. I mean, a quoted process. And there's a normalizer here that's akin to what goes on in the Rolang implementation.
What's a normalizer?
So it gives a normal form for processes.
Cool.
Yeah.
Makes sense.
Well, it turns out that this is unusual, right? There isn't a normal form for PyCalculus processes. But there is a normal form here if you assume a particular ordering. And I've given the ordering here, so this is the order. And I can't remember how I did. I think I put inputs in front of outputs, and so on. You can just read the code to see how the thing is ordered. Basically, I've tried to do it in terms of complexity. How much risk, how many parameters are in a particular term. And so then you can turn things into a byte vec, basically. So that gives you the code for that. Anyway, the point of walking through this code a little bit is just to see that it is in fact practical. That you can actually take this recursive knot tying approach and write code against it. So that gives you some confidence that the implementation is actually something that you could potentially put into production. There's a lot more to it than for production quality code, but that's kind of what I was getting at, is that at the end of the day, part of correct by construction is that the math becomes the code, and the code turns directly back into math, and that's what I'm demonstrating here. So that's why it's really important to go, when I'm suggesting these kinds of exercises. I really want people to take it seriously, in the sense of like how could the math literally become the code and not just be a guide for the code. It's a different methodology, right? And that's the kind of methodology that we see in languages like OCaml and its parent language SML, and likewise in Haskell. It's available in Scala, but that's not really Scala's core design philosophy. At least not as I see the language design. There's too much of Java still hanging around in Scala that that the essential methodology of the language is that the math becomes the code. But this is certainly the approach that we're attempting with Rolang and with most of our chain. Okay, so any questions about that? I thought it was important to kind of go over the homework a little bit and talk about some of these issues. Did anyone else see? I know I got something from Glenn. I know I got something from Phil. I know Jake's been coding. Who else sort of attempted the exercise and struggled with it or had questions? Or
Jake has a pretty substantial amount of code that I saw.
Mm-hmm. Yeah. Yeah. Yeah, I acknowledge Jake's, or that my intent was to acknowledge Jake's work there. Just wondering if there was anyone else who had attempted it and ran into questions or issues.
Yeah, I haven't yet to a full degree, but I'm make another attempt.
Okay, good. It's really important because, for example, in the Casper work, the whole at least all the stuff that Vlad is doing is based upon some initial domain equations that I wrote down for the message structure and justification. And you'll find that there's an implementation that goes all the way back to about 2009.
Seriously?
Of that structure in Scala that I put into production. That I put into production. So here I'll show you. Let's see if I can navigate the new. Let's see, special K. Yeah, if you go here into special K, and then you go into source, Scala, and then let's see. I think it's here.
If it's too hard to find, it's no worries. I'm happy to check it out.
No. This isn't. I think it's going to be under lib. It's not too hard to find here. Let's see. Okay, that's lift. I think it's probably under model then. Message. And here we go. I think it's here. Yeah, here we go. So we have messages have a notion of a header, and let's see, how does this all fit together? Yeah, okay, so there's a notion of a header, and then there's a notion of a message, which is parametric, and the justification and the body type. And the justification is optional. Here, let me scroll this up a bit. Is that readable now?
Yep.
Okay, there we go. So we have a body type and an optional justification, which means that you can kick things off. Like if you think of a server in an interaction with a server, like the first request doesn't need a justification. That's kind of what makes a server, right?
Right.
And then as you get rolling, then there's the history, which is the justification.
Very, very cool. That's so cool.
Yeah. And then the whole thing. So we have this notion of a request, which has a response as its justification, and then we have a corresponding response, which has a request as its justification. So we tie the recursive knot. And all of this was the core messaging for the special K protocol. And if you look, it was I think the last commit on, like, I hardened this around 2010.
That's awesome. Wow.
Yeah. And all of that is, yeah, so it was first created in October of 2009. And so all of this idea is derived, so that people understand, is derived from the justification structure in the Highland-Ong games. So Highland and Ong provide a notion of game that is used to give a fully abstract account of a linear logic. Full abstraction is kind of the gold standard for the semantics of a computational model. So basically, what it means is that if you have two different computational models, and you're giving an interpretation of one in the other, then let's call the one M1 and the other M2. Then whatever your notion of equivalence is in M1, it has to map into the notion of equivalence in M2. So that means that, and it has to faithfully map in. So if two programs are equivalent in M1, then they're equivalent if and only if the translation of M1 of the two programs are equivalent in M2. So that's the notion of full abstraction. And this is going to lead us, this discussion is going to lead us into some of the topics that we want to touch on next. But I just want people to start to begin to think about this in the context of correct by construction, so that we can, when we're thinking about giving interpretations or moving things from one model of computation to another, we want to sort of hit the gold standard, as it were, and understand how high a bar that is. Basically, it means that you just kind of shuffled the syntax around a bit, but the models are effectively the same in some deep sense. And it's also important to understand this from the perspective of expressivity. So, like, if you are unable to give a fully abstract interpretation, then you know that there's some jump in expressivity, or some gap in expressivity between the two models. So let me give you some relevant results for process calculi that help understand this kind of measure. A really good one is Katusia Palamadisi's encodings of choice. So this recently came up in some folks who were looking at the select construct in Rolang, and noticing that there's no corresponding encoding in the row calculus, or there's no corresponding syntactic construct in the row calculus. So I don't know if people noticed that before, but people in the class noticed that. But it's definitely a sort of a difference between Rolang and the row calculus. Now, it turns out that there was a folklore result that input guarded choice can be encoded into the choice-free fragment of the calculus. So, so to make sure that everyone understands it, does everyone know what I mean by choice?
It's the plus operator in the pi calculus.
Yeah, that's correct. Yeah, that's right. And you can have different flavors of the plus operator. Right. So you can have a flavor in which the only kinds of things that can be summed are input operations. Or you can have mixed choice, where you can sum inputs and outputs. So those are two different ways that you can introduce the choice or plus operator in the pi calculus. Those people are familiar with the plus operator. Does someone want to give an intuition as to how it reduces?
So when you have the sum, only one element inside of the sum is allowed to sort of be a term that reduces, and it can be non-deterministic. And once that reduces, the rest of the sum evaporates.
That's correct. That's exactly right. So if you look at the COM rule, there's the sort of the general purpose COM rule for the pi calculus actually includes the sum as a part of its apparatus. And what it does is it picks out, one of the inputs in one summand. So the general purpose COM rule for the pi calculus with summation is you have two terms that are in par, and both of them are sums, and one of them is an input, and the other one is an output. So just to be clear, you have a sum that has an input as one of its component summands, and you have another sum which has an output as one of its component summands. And then you reduce, feeding the data of the output into the awaiting continuation of the input, and getting rid of the other summands in either term or both terms at the moment of reduction. It's kind of interesting, just as a side note, I was speaking with Robin. We were having lunch one day at Cambridge, and I was pointing out that this looked remarkably like a formulation of a sort of compositional version of quantum mechanics. So if we look at the sum as providing the different superpositions of a system, then this is describing how you have two different systems in superposition, and you have a notion of interaction, which is sort of underlying measurement. And from that point of view, you get then when they interact, there's a corresponding this is the collapse, the sort of sort of famous notion of the collapse of the wave function, or a measurement. And then you get a new a system in a new state. Unfortunately, in the standard quantum mechanics, you don't sort of see the next superposition. but because of the formulation of the pi calculus, you do see that the whatever it results in is potentially a process that also decomposes into pars of superpositions or pars of summations. So anyway, I was talking to this to Robin about this at standing in the lunch line, and with a twinkle in his eye, he said, "Well, we wouldn't want to exclude that possibility, that possible interpretation of the pi calculus." So it was very clear to me at the time that he was thinking along those lines as well. Okay, so popping the stack a little bit. What's the point here? The point is that Catuccia Palomedisi proved that there's no par preserving translation of mixed choice sum into the asynchronous fragment. So there is for the input guarded summation, but not for mixed choice summation. And that par preserving criteria is effectively the kind of criteria that we're looking for when we talk about full abstraction. It's sort of a weak form of the full abstraction where the syntax rejiggering is not allowed to mess with the pars, and that gives you a measure of a jump in expressivity, right? So somehow the par, somehow the mixed summation, mixed choice gives some significant jump in expressivity in the pi calculus, and this notion of par preserving translation is a way to measure that. Likewise, to the best of my knowledge, there hasn't been a proof of a fully abstract encoding of the ambient calculus into the pi calculus. So to the best of my knowledge, that has still, to this day, since the earlier mid-90s, no one has presented a fully abstract encoding. And that's evidence, it's not a proof, but it's evidence that there's a jump in expressivity between the pi calculus and the ambient calculus. Somehow the ambient calculus is more expressive, and that makes sense because in the ambient calculus you can write down leader election as a one-line program. Now, interestingly, with the row calculus, you can also write down leader election as a one-line program. I in December of 2016, I presented a sketch of an encoding, a fully abstract encoding of the ambient calculus into the row calculus, suggesting that in fact there is that they share the same class of expressivity, and it's very clear that you have an expressivity jump between the row calculus and the pi calculus, because there's this higher order capability in the row calculus that's not available in the pi calculus.
Where would we be able to find that sketch?
It was recorded to. It was recorded via Zoom, and I can't remember where it was put, but I'll look for the link.
That'd be great. Cool.
Yeah, sure, absolutely. please remind me of the links that I promised you guys. Okay, so that's the sense in which this gold standard of full abstraction is it's not just a theoretical thing. It turns out to have this practical import that it allows us to measure when we have jumps in expressivity. And that's important because I don't know if you've been sort of noticing, but what we're talking about is being able to build up languages by adding features to sort of a core language. So in the case of the row calculus, the whole idea is that we start with something really, really simple, really, really basic, what we can express on a page. And then step by step, we add features, like the choice feature is one feature. The join feature is another feature. And the methodology of correct by construction is one in which we want to make sure that at every step we understand the sort of the semantic import of adding that feature. And full abstraction is the technique that we use, or one of the techniques that we use to um, understand, to check what sort of expressivity jump we've added to the originating calculus, right? Is it a conservative extension, in which case there's a fully abstract encoding of the new language with the added feature down to the original, or does it represent a significant jump in expressivity, like we see with the mixed choice, or the addition of locales or regions in the case of the ambient calculus versus the pi calculus. So let me stop there because I've said a whole bunch of stuff, and just check in and make sure that people are following to understand what the discussion is about, and what we're talking, what the how this relates to programming.
Yeah, I think I need to probably look at an example of a fully abstract encoding to understand what it is or what it looks like.
Sure.
And how you can tell something, the difference between a fully abstract and a not fully abstract encoding, and what the par preserving translation is. That's where my confusions are. But it seems like maybe.
No, that's good. That's really good. That's very good. So let's take a look and just see what the formulation is here. Okay, so just clearing off some workspace for us here. And so what we're saying is that P is equivalent. I'm going to use a funny. I'm going to use a funny notion, funny equal sign for equivalence. So P is equivalent to Q, and then if and only if and only if the translation, let's see, do I have that? Of course I don't have that. Parentheses, let's try it. Let's use these, I guess, as the close. Add to favorites and add to favorites. Okay, so what we're going to use is these funny brackets to represent the translation of P of Q.
Is it a separate notion of equivalence? Is it equivalence in the new language?
Yeah, so I'm going to subscript that. So this is 1. And this is 2. Okay, so there, that's the basic notion of full abstraction. All right, so P and Q are expressed in your original model. So let's give an example. So P and Q might be expressed in the lambda calculus. And their translations might be in the pi calculus. So then over here, the kind of equivalence that we might use is what's called Morris style equivalence. So Morris style equivalence says that basically P and there's no context. There's no distinguishing context for P and Q. So we talked about context last time. So if I take some context, some lambda calculus context, and I put P in it, then if it converges to the same value. And as if I were to put Q into the same context. And then over here, we might use bisimulation. And this is sort of leading up to a discussion of bisimulation. And so the notion of bisimulation is one in which if P can make a transition via some observation alpha to some P prime, then there's a corresponding Q prime such that Q can make an alpha transition to Q prime, and then P and Q prime are also bisimilar. So basically what that does is that unfolds the tree, and we'll go into the details there. And that's kind of the whole point of what we want to set up for next time. But I'm just trying to get your attention on this idea that there's a notion of equivalence in one model, like Morris style equivalence in the lambda calculus, and there's a notion of equivalence in another model. And full abstraction insists that if they're equivalent in this model, then they're equivalent, then their translations are equivalent in the other model, and vice versa.
So I guess in full abstraction, there can be many different types of full abstractions in that, like, Morris equivalence in one equates to structural equivalence in another instead of biosimulation. And would that be like a different flavor of?
So structural. So this is all. Full abstraction is all about the behavioral side. It's not about the structural side. The structural side is fundamentally about erasing syntactic differences that don't make a difference, and is not not typically used to encode behavior.
Okay, sure.
Yeah.
So, but there's still then like weak bisimilarity and strong bisimilarity, right? Like there's a couple different.
Yeah.
Yeah.
Yeah. So, for example, we might also have, instead of using Morris style equivalence in the lambda calculus, we could use applicative bisimulation. So, in the lambda calculus, Abramsky came up with this idea of a notion of bisimulation for the lambda calculus, where instead of par, you're using application. and that turns out to be roughly equivalent to Morris style equivalence, but it's a different formulation. And what it does show is it shows something that's very important about bisimulation, which is that bisimulation is a deep, it's a profound notion of equivalence that really deserves a great deal of study and a great deal of attention. There were some papers around the 2005 timeframe that showed that every known process equivalence factors through a form of bisimulation. So every known process equivalence, even if it's much coarser than bisimulation, like trace equivalence is much coarser than bisimulation, failures equivalence is much coarser than bisimulation. They can be turned into a form of bisimulation followed by some form of forgetting or identification. So that turns out to that gives us a sense in which bisimulation is somehow fundamental or foundational as a notion of equivalence. But to your point, Jake, we could, instead of using Morris style equivalence here, we could use applicative bisimulation over here and ordinary bisimulation over here, or we could use applicative bisimulation over here and say failure style equivalence over here. So yes, there are lots and lots of different full abstractions depending upon, because full abstraction is parametric in the two different forms of behavioral equivalence.
Great, thanks.
Yeah, absolutely. So I just want to remind everyone that the whole point of this course is to be able to come out of this being able to design these calculi. So I'm wondering if anyone has given any thought to designing a computational calculus. Is there a domain that you've thought, well, maybe I should write up a calculus for this to model my sense of what this computational domain is all about?
So I think it's probably already been done, but I'm looking at the linear logic right now, and there is, it has already been done, but I want to do that and understand that better by sort of writing it myself.
That's great. That's really, really good. So the Abramsky's paper, Computational Interpretations of Linear Logic, is he's done this a couple of times. So he does it for the intuitionistic version of linear logic, and then he does it for the classical linear logic. And proof expressions are the syntax for the classical version. As an aside, I came up with a variant of the pi calculus in which so we wanted to be able to have preserve symmetry in the take a step back. When we were designing Highwire, which was the precursor to Rolang, this was work I did at Microsoft. When we were designing Highwire, I was interested in, of course, passing data structures around and not just names. And I wanted the data language to be terminating. So when we passed data structures around, we wanted to be able to prove that the communication of the data structure would be terminating. And this was before I had discovered the row calculus. So the thought was to preserve the symmetry of PAR in the passing of data structures. So we used proof expressions as the means of encoding or representing data structures because we could prove termination and preserve the symmetry. So you can have variables in proof expression terms on the left or right hand side of a par, and so when you reduce, the substitutions are on both the left hand side and the right hand side, and this is ultimately what led to the special K idea, that you use prologue terms. The prologue also has this nice symmetry about the unification of the terms. The proof expressions, because they come from linear logic, have some additional features about resource constraints on the information that's passed between the two. But that sort of gives you a sense in which you can embed or combine these kinds of calculi together. Right, so you can build a variant of the pi calculus in which the proof expressions of Abramsky's computational model for classical linear logic and its corresponding reduction relation are sitting at the COM rule for the ambient not the ambient calculus in the Cardelli sense, but the containing calculus that uses the proof expressions as a representation of data. That's probably a lot to swallow, but it might give you some context. Any other thought about computational calculi that people are interested in? Nate, have you thought about encoding the Casper in a calculus style?
Yeah, so I guess the thought that I put into it has mostly not been from the point of view of creating a calculi, but more so of can we encode or can we write a Casper program, specifically in RoCalc. It's something you gave a pretty compelling argument for a couple times at this point, at least that I've seen, and so it's definitely something that I think we're interested in doing at some point in the future, especially because it especially like representing and then giving the safety proof in terms of this representation would be, I think, really kind of educational and useful as well. So yeah. Haven't made too much progress towards that end, but it's definitely something that's on the roadmap.
Cool. Yeah. I mean, so I wrote down sort of a very general purpose structure. I think it was in November of 2016, where I gave a deduction system style presentation of what I thought was going on with Casper. But there was, but at that point we didn't have the notion of safety, the decomposition of safety that Vlad had given. So there was the sense in which to constrain the calculus for the right consensus properties was still very much under investigation. And I never went back after Vlad had proposed safety to look at that. But I think the more generally interesting question is, how does the safety proof carry over when your states are not just sets of messages with justifications?
Yeah, totally.
but are in fact programs
Yeah. I mean, I guess the easiest thing to do, it seems, would be to represent somehow, like having an accumulator and a way of like translating that into a set. I don't know if that makes a ton of sense, but I feel like we could imagine having protocol states as sets in a way, if we could implement that as a program. Sorry, my dog was getting sick, so
no worries. No, so I again, what I would really want is that program states are processes, but then it becomes interesting because you drop, and I think recently Vlad's presentations do drop this whole category notion, like the one that you and Vlad and Georgios wrote up. It drops the idea that the states form a category.
Yeah, we definitely. I think there's like we ran away a bit from the like categorical language, etc. For sure.
Yeah. So that's interesting. All right, we're at the top of the hour. So I'm gonna throw out an exercise before leaving, which is write down a computational calculus style presentation of the formation of the Arabic numerals, so 0 through 9, 10, and so on, and an operational semantics for addition. So we want a
cool.
Yeah, we want the grammar for the numerals, and we want an operational semantics for addition. And for extra credit, do it for Roman numerals.